And we're now looking at finding shear and moment diagrams by finding the equations. And we've already seen this problem. Earlier, we found the internal forces at C, and we found that the C normal force was 0. The shear at C is 10 kilonewtons, and the moment at C was negative 20 kilonewton meters. Okay, so we found that at C. Today, we're going to actually write equations for the two sections of our beam and calculate the shear and moment equation so we can draw the diagrams and then check to see if these values at C were correct. At C is just a snapshot of one particular point in the beam, but we have to understand forces and moments are all the way through, okay? So how do I know where I need to draw my line for a shear moment diagram? It's a great question. So to start, what you may want to do is take a blank sheet of paper or a Post-it note, start at the left and slowly move over, okay? I can see that's a constant. Oh, I've had a change. Okay, I had the addition of this 50 kilonewtons. I also had the ending of that uniform load. So this is going to be my second segment from 2 meters to the end of the beam, which is at 4 meters. So we now know that we're going to have from 0 to 2 meters and then 2 to 6 meters because X always starts at the left side of your beam and includes everything up to that point, the midpoint between where we've had changes in loads. So what do we always have to draw, friends? We always have to draw a free body diagram. And I'm going to lay this here because we're going from 0 to 2 meters. So as I'm moving across, I can see it's a uniform load as X is increasing towards the right. So I have X. And I know internal, I could have a normal, shear, bending moment. Again, we use positive beam notation because we're looking at behavior. And we have this distributed load of 20 kilonewtons per meter. So as we're increasing, the area of this rectangle is increasing. And so we can make that be a function of X. So I also know that if the base of this is X, that the centroid of a rectangle at any given moment is just base divided by 2. So this is all we have from 0 to 2 meters, and we've just cut it somewhere in between 0 and 2. So let's sum the forces in the y direction, and we know they equal 0. So I have 20 kilonewtons per meter times x meters. Okay, we're not actually putting this value of 2 because we're somewhere between 0 and 2. That's a negative for direction. Minus my shear equals 0, so my shear equals negative 20x kilonewtons. So that will describe the changing in my shear as we move from 0 to 2 meters. Then we're also going to do the same for our moments. We're going to start at the left of the beam, and we can see that this distributed load is going to cause a moment about my cut. And as we get larger here, our load gets larger, and so we need to be writing that as a function of X. Again, the area under the curve is base times height, so we have negative 20 times X. That gives me the area, and then X divided by 2 gives me that distance to my cut. And that's the only thing externally creating a moment. Internal, the shear and normal at this point don't affect us. And then we have a positive moment. I don't know why I want to call that negative, but we are using right-hand rule. Okay, right-hand rule. So counterclockwise is positive. So positive rotation. All of this equals 0. So we get that our moment then is negative 10x squared kilonewton meters. So this is our moment equation as we travel from 0 meters to 2. Okay, we did that part. Now we need to look at the second segment. Again, we always start at the left and move our way over. There's the first segment. It's now going to be the full 2 meters that we're using. And here we move from 2 meters to 6 meters. Okay, we're adding everything up. So 2 meters to X to 6 meters. So starting at the left, I have to make sure I include all of this distributed load now. at 20 kilonewtons per meter. I have to make sure I add this 50 kilonewtons that's coming in at A. We're going to have internal shear, normal, bending moment. X goes all the way from the left to my cut. I know that this amount is 2 meters, and now we get to see that whole 2 meters. And so if I want to find the value of from my cut back to that 50 kilonewtons, if this whole distance is X, then this whole distance is 2 meters. This has to be X minus 2. So we are going to set it up the same way. We're going to sum forces in the y direction equals 0, and we've got negative 20 kilonewton per meter. This time we have the whole 2 meters. Okay, we've included all of it, plus 50 kilonewtons, okay, minus V equals 0. And again, I've shown positive for behavior, but it is negative when I start using my equilibrium equations because I am calling up to be positive. So this is statics, equilibrium, this is behavior. B equals 40 kilonewton meters plus 50, well, I took rid of that meters, okay, plus 50 kilonewtons. So my shear equals 10 kilonewtons, okay? So that's a constant. When we graph a constant, it doesn't matter where I am between 2 and 6 meters, I'm going to have 10 kilonewtons, okay? Now let's sum our moments about our cut. Again, right-hand rule. So here's my cut over here by my finger. Okay, I have 20 kilonewtons per meter times my base, 2 meters, so this is the force. The moment arm. We know that the moment, okay, the force acts through the centroid, which is right here. So to get back to that uniform load, we have to walk back x minus 2. Then we have to walk back halfway down this length, plus 1/2 times 2 meters. Okay, 50 kilonewtons. Negative 50 kilonewtons, it's creating a negative moment. Its moment arm is x minus 2. Nothing else till I get to the moment plus moment equals 0. So I get that my moment equals a negative 40 times x minus 1, okay, plus 50 times x minus 2 equals negative 40x plus 40 plus 50x minus 100. 10x minus 60. Okay, so now what we can do is kilonewton meters. To go back and graph, it's just basic geometry at this point. Okay, as I'm going between 0 and 2, so this segment, I know that my shear is negative 20x, and I know that my moment is negative 10x squared. So when x equals 0, my shear equals 0. When x equals 2, my shear equals negative 40. Of 0, negative 40. Okay. Over here, I have that my shear equals 10 kilonewtons from this point, from 2 to 6 meters. 10 kilonewtons. Okay. So this one is constant. It doesn't matter where I am. That's a constant. This is a function of x. It's linear. So I know as I'm going from 0 to negative 40, it's a function of x. So if I decided to put x equals 1, which is right at that midpoint, then I would get that my shear is negative 20. So I can see really quickly that we have a linear relationship. And what we're going to notice is that up here, I have a load that's linear, it's constant. And what happens when we integrate a constant? Okay, we end up getting a 1-degree curve. It's linear. Here, I don't have any loads affecting. It's constant all the way across. So what we find is that we end up with a constant. or a 0-degree curve. What do you think is going to happen when we find our moments? So here, from 0 to 2 meters, I have negative 10x squared. When x equals 2, my shear equals 2 times 2 is 4 times 10 is negative 40. Oh, okay, so negative 40. I don't know why I called that shear when clearly that's a moment. Again, it's been a long day, friends. Okay, and when x equals 6, I have, okay, just restart this whole thing. We are going from 0 to 2. When x equals 0, my moment equals 0. When x equals 2, my moment equals negative 40. Okay, negative is below. I've got my units on here already. Okay, now over here, our moment equals 10x minus 60. When x equals 2, our moment equals negative 40. When x equals 6, our moment equals 0. So we are starting at negative 40. We're coming up to 0. What do you guys think the shapes of my curves are going to be? Based on constant to 1 degree, nothing to 0 degrees, where do you think we're headed? If you don't know, all you have to do is go back and say, well, when x equals 1, my moment equals negative 10. Here's 1. So I can see very clearly that this is a parabola. It's a function of x squared. We now have a 2-degree curve. And as I'm going from negative 40 to 0, if I don't know how I get there, halfway point between 2 and 6 is 4. So I can say x equals 4. I get negative 20 right here in the middle. This is a straight line. It's a linear relationship. This one was parabolic. Okay, this one was constant. This one was linear. That's the cool thing about these graphs. Once we start doing them based on area of the curve above, it's pretty easy to start seeing where we're headed. And this is a great way for you to start understanding, number one, your equations, and number two, do your equations make sense? Here, I went from 0 to negative 40. Okay, all of a sudden, I added a 50 kilonewton load. Negative 40 plus 50 is 10. From the 50 to the 10, I'm not changing anything. Whether I cut it here, 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 I'm going to have the same internal shear. When I'm looking at my curvature here, I can see that I have a negative area. And we're going to find that a negative shear area gives me a negative moment curve. I'm heading down. All of these things are interrelated. Right now, you need to focus on figuring out the sections of the beam, your free body diagrams, writing your equations, and then using your equations to figure out what the shape of your curve looks like. Make sure you're visiting with our TAs if you need help. This is super important. Okay, I'll be moving on to the next video. Good night.